Hello everyone and welcome to our Summer of HPC project presentation. Nelly and I have been working all summer on Project 2002, Neural Networks in Quantum Chemistry, and would like to share our progress and achievements over the course of the project. Our task was to investigate the application of neural networks in quantum chemistry. In essence, chemistry is the study of molecules and their complex reactions. Molecules themselves are building blocks of the universe, and while not the most fundamental unit of matter, they play an important role to technology and human civilization as a whole. Molecules may be as simple as water or as complex as myoglobin, and they may also have a periodic structure in what we call crystals. Molecules are collections of atoms, bound together by the electrostatic forces of the particles that make them up. It is the structure and nature of these atoms that give rise to the molecular properties one witnesses. It is important that we study these properties in order to find potential applications, anywhere from material design to medical effectiveness. Some of them may include the electric charge density, the internal or free energies, as well as the highest occupied and lower unoccupied molecular orbitals and their energy gap. The true nature of these particles is quantum, and therefore calculations require a similar approach. Calculations in quantum chemistry often utilize density functional theory, or DFT, whose time complexity unfortunately scales exponentially with an increasing number of atoms in the molecule. Several open source and proprietary calculation packages exist to aid scientists in the field, and we present some of them below. In order to circumvent slow calculation and aid in materials and medicine discovery, we turn our attention to neural networks. Neural networks are machine learning algorithms which can approximate any function when given at least two layers and a nonlinear activation function. They have been used in various fields and successfully aid solving a myriad of problems, defining abstractly while also finding patterns hidden in the data. One important decision we must make in order to ensure success is a meaningful selection of features that correctly represents the physical system under study. We should ideally cover the configuration space completely and have no degeneracies, meaning that every molecule in the dataset is to be represented uniquely and fully. We achieve feature extraction with the help of an open-source Python package named Describe. It includes algorithms for methods proposed in state-of-the-art papers, such as the smooth overlap of atomic positions, or SOAP, which expands a power spectrum series using a Gaussian approximation for the local atomic density projected on the spherical harmonics. Atomic Center Symmetry Function, or ACSF, which fingerprints molecules by projecting them on various 2- or 3-body functions while retaining no elemental information about the center atom, and Many-Body Tensor Representation, or MBTI, which returns a highly interpretable distribution based on structural motifs, allowing it to also function with crystal structures. In order to train our network, we require a clean dataset with accurate calculations, and for our purposes we use the QM9 dataset, commonly used in the literature. It contains 17 different properties for 133,885 organic molecules calculated using the P3-leaf method of DFT. The properties presented include rotational constants, dipole moments, and various energies at room temperature conditions. Because featureizers act on individual atoms and not the molecule as a whole, molecules with a different number of atoms form output vectors of varying size. These are unsuitable for training, and Describe offers to average all the values out. Instead, we implemented a Python method which averages by the type of atom, thus retaining more of the information extracted by the featureizer. In this example, we use SOAP with a maximum principal quantum number of 4 and a secondary number of 3, which are sufficient given that only few heavy metals are present in the dataset. The topology used downscales the input vector by 2 powers of 2 on each layer before arriving at a single output vector for the Gibbs free energy at room temperature using a batch size of 128. Training used a variable learning rate and was stopped prematurely after 93 of the total 100 epochs to prevent overfitting. We notice a spectacular feat of the data, yielding a root mean squared error of about 24 Hartree, 2 to 3 orders of magnitude less than the actual calculated values. We performed additional tests on the time efficiency factor of this approach. First, we retrained the same network after disabling the GPU, which resulted in more than double the time taken, indicating that GPUs offer substantial speed up when training. Furthermore, when featureizing with Describe, it is often advised to enlist more CPUs to the task. As evidenced by the figure, the time taken is inversely related to the number of processors used. Now, I will hand it off to Nelly to discuss even more featureizers and network topology.
By using different descriptors, that is, the types of features used to describe a molecule. We tested 3 descriptors, colorimetric, SOAP, and ACSF for prediction of Gibbs free energy on the same neural network topology. Descriptors differ in the number of features used to describe a molecule, therefore on the complexity on the input data. We found that with the colorimetrics, there was an excellent correlation between the predicted and the true values in the test set with the used neural network topology, while SOAP also gave reasonably accurate parameters. This was a very welcome result, since colorimetrics is the most simple of the 3 descriptors, therefore we can get good prediction using neural networks with less parameters, which also results in faster training. We also tested 3 topologies. Here the loss function is plotted against the number of parameters. The predictions were successful for coulometrics even with smaller networks, while changing the topology did not improve runs with SOAP and ACSF. To conclude, in this project we constructed a neural network that could give a good approximation of Gibbs free energy, which is a very efficient method compared to quantum chemistry calculations. We found that GPUs significantly boost the performance of neural networks compared to CPUs. However, to get a good prediction with neural networks, there are many optimization steps required. First, choosing the type of descriptor and fine-tuning it, and then adapting neural network topology, learning rate, and other parameters. Thank you for your attention.